models. So usually in control industry, we use for different kind of uh, work, there are different kind of models. Some use black box models, some use white box model, gray box model. So my PhD is focusing on how to use data-driven models, black box models. So in building industry, I need to predict for controls. I need to predict the indoor temperature or some other uh, um, parameter about a room, about a building, for next at least 1 day. That goes in the model predictive control, in the horizon control, and it determines the best options for controls for heaters, for supply temperature of air handling units, for chiller and or boiler working. So we need to predict some future time steps, and research says that it has to be at least 1 day. So with this, I think LSTM was the best thing I could use to predict next 1 day of some data. For example, we can use sequence to sequence model architecture.
Gaurav,
And this, yes,
can you make your screen full screen?
yeah, yeah, now it's good.
Yeah, thanks.
Yeah. We can use the sequence to sequence model architecture, which Professor has already talked about. So I don't need to go more into it, but it's pretty explanatory till now that we put a sequence and we get a sequence out. And both the incoming sequence and the outgoing sequence can have different length. Um, of course, in applications, for example, in chatbot and text generation, there are dynamic um, sizes of sequences, but there's a theory behind it, and we don't need to go there. But right now, we are only focused on fixed incoming sequence and outgoing sequence. So this slide, I think we have covered in detail before, so I didn't to discuss here. Um, but there's another problem which is very difficult to understand. So when you say that x1, x2, x3 is taken as input and y1 and y2 are the output, for example, this is the number of features and this is the number of outputs. What do we mean by number of cells in LSTM? Because in LSTM, in Keras, we need to put number of layers. So what does number of layers mean? Is it like 3 layers? But usually the inputs are like from 50, or like it can be anything, but people put 50 or 100 or 200. So what does that mean? So what exactly means is we take the xt minus 1 um, and we run it those number of times. So this is split into that recurrent um, state as we saw some time ago. And so number of units actually represent that one LSTM cell is run that many times. So if its number of layers is 100, so it will be run 100 times. Um, yeah, so basic code encoder decoder looks like this. So you put all your inputs on encoder side. Um, there is a LSTM cell for each of the inputs. Number of units, number of layers decide how many times it will be run, one LSTM. So LSTM takes the time series as input and creates the encoding of the input sequence. This encoding goes into another layer called encoder layer, and this just makes a vector consisting of all the hidden state and the cell states of all previous LSTM cells. This encoder goes as the input for the decoder LSTMs, um, and then comes the output from other side. But studies have shown that you can put multiple LSTM layers, and that might help a lot to learn complex patterns if there are. So I started playing with both of them. Of course, double LSTM encoder and decoder was working a bit better, but the matrix sizes and the was getting too large. So my computer gave up. So I had to reduce the size, and then I shifted to just one LSTM based encoder decoder. especially for this is not important. So today my target is to show you basically the matrix manipulation behind input and output data, and then how we train it, and then what we do with that data. We have already gone through the number of neurons and number of other mathematics related to LSTMs, but I can just show you how we go through the data. So I will go back and I will share my input data file. So for example, I have input. So this data was generated using a simulation program. So this is a white box model data. So I designed a building and I ran energy simulations on it using a program called iDice, and it generates 15 minutes data for the whole year. So this is going all the way until 31st of December. So there are 35,137 data cells. So what data do we have? So right now we have temperature of outside, relative humidity outside, wind outside, solar radiation outside. So these four becomes the climate related input data. Then there are two time related input data. So hour of the day and then day of the week. So day of the week, I have just started from zero on Monday, uh, but it can be anything. It doesn't matter. But it has to be numbers. So you have to convert everything into numbers. So then hour of the day and day of the week. Then there are four zone specific information. So this is the equipment load in the zone. Zone, I mean a room. Um, I mean a room in a building. Zone is a term for thermal zones in building industry. So zone is equipment data, zone 8, and then zone 8 other has HC, which is heating and cooling data, and then light in the amount of light watt in the room and the occupancy in the zone. Um, and then same information I have on other zone. And then I have the inside temperature in both the zones. So zone 8 and zone 12. Right now, I'm showing you a very small data set of only two zones, but usually I have to do a study where there are almost 36 or 40 zones. So it becomes a lot of input and output. So this is the data I have. So now how to split it into input and output. So I know for sure that, okay, these are all gonna be inputs, but LSTM can also take um, the same input. And so these are input for sure, and these two are outputs, which I want my LSTM to predict. So we can also give the same input of previous time step as the same output as the input. So this all becomes the input for sure. And next, and then for the next step, this becomes output. So how to go forward with that? So before going to step 2 here, I'll show you the script, which we can see how it works. Yeah, so there's nothing here. It's just downloading the data. So in the data, I have all which I showed you right now. So what is the data shape? Right now is 35136 by 16. So 16 was the number of features, as you can say. Next step is I scale everything from 0 to 1. I find in every column, I find the minimum and maximum, and I scale everything from 0 to 1. Scaling helps a lot to in the training. Without scaling, everything goes bad. Um, yeah, the scale, and this is all the scalars, just to see them. Then after scaling, it looks like this. Next, I just split it into training, validation, and testing data. So I have done 60, 20, 20, and just some array manipulation, and I get 3 arrays of, as you can see here, training, validation, and testing. Yeah, this was just to see how does all of them look. All good here. Yeah, now my next step is to convert this series of samples into supervised learning um, data set. I think some of it we had discussed in the presentation, but I'll show you in a bit different way. So this is the kind of the function which professor also showed us before, but it does the same work. How does it work is, I'll go through it. So we run it. So first I pass my data set into this function, and I write the number of past steps I want to take as the input, a number of future steps I want to predict. So for my for today, I'm taking 384 past. 384 is, so my data is in 15 minutes. So um, if I divide it by 4, which is the number of 15 minutes in 1 hour. So this is 96. That is divided by 24, 4 days. So I'm taking 4 days of data as the past. 48 is half of the day. Right now, I'm just reduced the 48 divided by 4, which is 12 hours. So I'm only predicting for 12 hours, but my study, the paper which I'll be submitting is for 1.5 day and so on and so forth. But right now, to just show all the matrices, and I have reduced the size. Okay, so we'll pass the training data set in this matrix. We'll put 384 here and 48 here. So, and then we'll see, and then it splits out two arrays. First becomes the uh, training data set, and second becomes the, sorry, first becomes the input train, and then becomes the output train. And then we see the shape of the size. So it is 20689, then 384 is the history time steps, past time steps, and then 16 is the number of features. And Y train also becomes this. So if we look in our Excel sheet, so what that thing does, it copies the whole thing and put it after this. And it and the next step I'm going to do is I will delete. So in the next step, I go and delete all these lines, because so this is the X train, and this is becomes the Y train. And I delete the ones which I don't need as an output, because output is only the temperatures of two zones. In the next step, I delete, yeah, sorry, before going to the next step. So what it does is it makes 384, that is the past steps. So it takes, for example, if I take 10 steps of the previous, it takes this block, and then it takes that 8 blocks after this. 8 is right now the future steps, and 10 is the past steps. So in my code, 384 is the 10, and 48 is this 8 here. So it takes this data and makes it 1 multiplied by 8 multiplied by 16. And this keeps on moving. So then the next one becomes this. It adds into it, and this becomes 2 by 10 by 16. And then it takes the next 8 here, and it becomes 2 by 8 by 16. And keeps on doing it until it reaches the end of uh, the the training set. So then it becomes that large number, which we saw in the code as this large number. So it goes all the way until down here, wherever the testing is until training is until. So, so as you can see, this big number multiplied by history multiplied by 16, the number of features. So you see this big number multiplied by history multiplied by 16, and then this big number, future, and then 16. So my testing, my output is still 16. I don't need 16 values. I need 2 values. So I did this. Uh, I wrote this code to delete these middle ones. So I don't need this data. So in the next step, we delete all of that, and then we are left with that big number multiplied by future time steps multiplied by 2. So we run this thing, and we get X train as 384 by 16 and Y train as 48 by 2. Then I do the same thing for test validation and testing. Yeah. So now, if things are clear with this, we can move forward. But either you guys can tell me or we can discuss it later if things are not clear that place. Is it all good?
Yeah, this is fine. Any questions, please? No, so it looks okay.
Oh, yeah. So the next is making the model architecture. This is the model which can be seen here. So we have the LSTM layers, and then the data goes to the encoder state, encoder layer. From the encoder, it goes to decoder LSTM and then output. So I write the code for the model architecture here. It takes n, the shape we have to determine using the n passed number of features and number of layers. So all these hyperparameters I have initialized in the first line. So number of layers I have started with 200. I have put also a dropout factor of 3.3. So 30% of the random states will be deleted. Epoch I have kept to 50 and batch 32. So once we make this model, and we can also visualize it. Uh, Although I'll open it in a simple way here. Yeah. So the input layer, the input layers get this out in as 384,16 and that big number. That splits it into three different 2D matrices. One goes to the repeat layer, one goes to the decoder LSTM, and decoder LSTM takes the repeat vector, which is the encoder vector, and also the inputs from encoder LSTM. Then decoder LSTM uses time distributed dense layer to split the data into 48 by 2. So 48 is a feature time step, and 2 is the number of features, number of outputs. I go back to my, yeah, so we do this. I'm not going to train the data right now, but I have already trained it. But I can show you what things I have used here. So you can use
Can you
different types
explain the
of
model one more time,
callbacks.
please? Can you go back to the model? The code.
Yeah.
No, the code. You can just explain this one step by step, please.
Okay. I'll do this so that it's a bit more clear. Yeah. Okay. So LSTM in the encoder LSTM. First, we had to make a input layer. So this is a very straightforward input layer. The number of past steps and number of features. The number of features for us right now is 16. Then encoder LSTM takes the number of layer as the input, which is 200 right now. We include dropout factor, and we also have possibility to set if we want the state to be returned for the next LSTM. So as I said before that, this means that LSTM will be run these number of times, 200 times. So in there you have an option if you want to give the state of one time into the next time. Why this option is here, although this is like very fundamental property of LSTM that state transfer happen. But with time, people realize that some of the control industry or some different industries don't require state to be forwarded. And that's why I think they put this here function. Yeah, so now the input, this was, yeah, output and output one. Yeah, and then just let me go through it once more. Decoder inputs is Yeah, this was a bit of a confusion for me also to understand the way I did it first time with the help of someone, but um, it, the way the code is written here is that you have to write the input and output for all these blocks, and you have to uh, target them to the right place. So for example, LSTM layer would have three outputs. So one of the output has to go to the repeat vector, uh, and this is the repeat vector. So it takes the first output of encoder layer. So encoder output 1, 0 goes as the input for repeat vector. Then the second output of LSTM layer, second output can be seen as this one, I think. Yeah. So encoder output 1 after 1. So not the second output, both the second and the third output. So after 1, it goes as, so as you see, encoder states 1, it goes as the initial state in the decoder LSTM. And it also takes input from the from this repeat vector. Then the output of decoder LSTM goes as the input in in time distributed layer. So decoder L1 goes as the input in time series distributed. Yeah. Uh, I hope you got it. It was difficult for me to also understand, but
Yeah.
um, the way
So
arrows are here,
so
yeah,
we feed the states. We just feed the 200 states, but
yeah.
it's only yeah, yeah. But it's only three times 200, right?
Sorry.
I
Yeah,
mean,
yeah, it's 3 times 200. Yes, yes, yes.
why exactly why the output is three or not? Why it's a three? Where did you decide it here?
So it is the um, so the output of a LSTM is
Mhm.
uh, yeah, this thing. So the output is um, so input becomes that 200 matrix. Then the output is
Mhm.
the output of the block and the states,
Mhm.
and the same output also goes as the in another copy.
As
So another copy of the
mhm.
output goes as the output for the next LSTM. So that's why there are three 200. So 200, 200,
Mhm.
200.
Mhm.
Yeah, so that's what these three 200s represent. So one of them goes as the state for the repeat vector, and then yeah, that's how it goes.
Mhm.
And in the last LSTM, in the encoder LSTM, it takes the same. Wait, what's happening here? Yeah, in the last LSTM layer, it takes all those three 200s. Yeah, and output is again three 200s, but we don't use all of them. We only use the output. We don't use the copy of another output, and we don't use the previous states. So that becomes output. So 400 by 200 becomes the output, 48 by 200. Then time distributed layer takes out and converts this 3D matrix of something by 48 by 200 into 48 by 2. So it goes through every line and records those as two inputs, two outputs. Yeah. Then if it's okay, then I can go how the training was done. Yeah, I guess I can just go there. Right now I have commented this line of code, but so you have option to put many callback functions. For example, there is a learning rate scheduler, which what it does is it reduces the rate of the learning if learning happens very slowly, or it's not learning anything. So it tries to reduce the learning rate so that it can come to the minima or maximum of the function. Then there's another which reduces the learning rate on a plateau. Then there's early stopping, which I think we have discussed a bit before in the presentations. So I think this is one of the best functions I've used. So instead of doing 50 epoch, it tries to find the best answer before 50, because I've seen that after a while, both the testing and the validation errors become plateaus out. So we don't need that time which we have spent there. And then LSTM examples, a lot of internet uses Adam as an optimizer, and loss function as this Huber loss function. This is the fit function. You have to put your training, both X and Y for training, number of epochs. You also have option to put validation data, although you don't need to if you don't want to have validation also. And then you can put callback functions. But there is a good library of callbacks if you want to use, and they are very interesting to go and check. But there are a lot of them. Um, and then I just make a history out of them, and then I save the model in .h5. So for now, I'll just use the h5 model which I trained before. So I'll upload the h5 here, and then I predict, and let this finish. Yeah. So now let's see the shape of the prediction. So the prediction comes out to be 48 by 2, and our testing was also 48 by 2. So now we have to compare them. So this problem, I don't know how many of you are actually going to be using sequence to sequence, as in we have time steps to predict in the future. But the way forward I have gone is I have found, so I'll go through it and then I'll discuss. So I just decide some things here. So I have both the predicted data. Now the predicted data is in 0 to 1, -1 to 1. So now I need to convert it back into meaningful data. So I use the scalars from before, and I call them back, and I put them through a loop, take the predicted data and scale it back to what it was. So I scale it back. Now let's see the scale back is the same shape. I was just printing out shape many times to just understand how things are going. So this E1 D1 is the after scaling. So we see that it predicts 2 temperatures for next 48 times, and then after that, and then after that. So if I also predict the scaled test data, so now we can see how was our prediction happening. So it was predicting as 19.9 and 21. It was supposed to be 20.4 and 21.5. So here there's a difference of 0.4 or 0.35, no, 0.4 degrees. And here is a difference of almost 0.5 degrees, and so on and so forth. So so usually in building industry, we use 3 data matrices, MAE, mean average error, root mean square error, and mean absolute percentage error. So I just used the math library and sklearn library, and I open these matrices. I calculate the the error between 2 values and record the data. So here I'm just doing the error, and I split the data into, like, for example, for zone 8, for time step 1, what is the MAE, and all these 3 errors. So this is so when it was predicting, it took the original data as the testing data for that time step for that zone, and compared it with the predicted data of that time step and that zone. And and it did it for the whole testing period and find the MAE for the whole testing period. So we can clearly see that for zone. So why I was selecting zone 8 and zone 12, because in my building, zone 8 is kind of a big living room, double height living room. And it's a big room, which is much difficult to control by heating units. So the temperature moves a lot up and down. So zone 8 is super, not random, but the temperature swings are very high. And in zone 8 is a small bedroom in the house, and temperature swings in the zone 12 are much more constant. So there are two different extremes in the room. So we can clearly see that zone 8, it's much harder to predict. So when we increase the time step, so we start from time step 1 and MAP of 0.94, we see that MAP increases all the way until time step 48 to almost 2 degrees. For zone 12 is much easier to predict. So we start from time step 1, which is MAP of 0.4 to just 0.5. So zone 12 is much easier to predict. And then there are just few line of code. So it saves the predicted and the test IIT
But
indoor air temperature for each
can I
time
have
step.
can I have a question about the time steps? So you trained
Yeah.
did you train a model for each time step, or you have a model for each time step? Because now you trained your encoder decoder for 48 in the future, time steps in the future.
Yeah.
So this is a model which
Yeah.
has been trained for
So
48. So if I want to test for time
for
steps
48
equal
future time step, yes.
47, yes, in this case I need to train a different model, and for each time step it will be a different model, or it will be the same model.
That becomes a different model if I need to predict 47, because then the matrix sizes changes and all
Mhm.
the these numbers change. All these
Yeah, I mean in the
number of
calculations here
parameters change.
I mean for the mean square error, mean absolute error, those numbers, you calculated it for
Yeah,
each time step,
yeah,
which means you have different
yeah.
predictions, you have different model. You trained 48 models. Is this correct?
No, it's not 48 model. My model is predicting is giving out a 3D matrix, and that
Mhm.
3D matrix I used to calculate three errors. So it's not 48 models. It's just one model which output is a 3D um, 3D matrix of uh, timed zone data and time step.
Oh, okay, I understand. Yes, thank you.
Yeah. And then there are just few scripts I made to record the data to see how the error matrix is changing with time, save predicted, and test IIT for some time steps, and so on and so forth. But I can show you how the testing looks like in terms of. So if we plot so for these two zones, if I plot the three errors, so MAE in degrees, I think yeah. So MAE in degrees Celsius, RMSE in degrees Celsius, and MAP in percentage. So we can see that zone 8 is clearly not a bad, I would say bad zone, but difficult to predict. And zone 12 is much easier to predict. So all these three numbers increase at the same rate. So by intuition, it makes sense because it would be much harder for a model of any kind to predict more in the future. So it's easier for the model to predict a bit nearer in the future. So it can predict good for next 2-3 hours, but then it becomes a bit difficult. Of course, now these numbers look very small. So every industry has different kind of. So for some people, or they're like, oh, it's just 2%. It's very good. So maybe industry wise, these numbers change. So for me, everything below 4% is good. 4%, and everything below 2 degrees is good. 2 degrees is still a high number, but below 1 degree is very good. If I'm able to predict below 1 degree, it's nice. Now, so these were the errors. I can also show you um, how the I can try to see if I can find it. Yeah, I think it's this one. Um, so how does the data looks like? So let's do this. Yeah, so I have predicted. So I have 48 time step. I'm not going to show you 48. I'll just show you 3 time steps. So 5, which is way nearer to the current time, 24, which is 6 hours ahead, and 48, which is 12 hours ahead. So let's plot 40 time step 5 for zone 8. So predicted and the actual, and see how it looks. So I'll also split this by, yeah. So we can clearly see that for zone 5, for zone 8, for time step 5 in the future, so 5 time step in the future, it's able to do some kind of prediction. It's not able to predict the peaks, the sudden peaks which happen, or it is predicting that there were peaks and there were not actually peaks. Um, but at least it's able to capture the swing as in the general trend of the movement. So this is for zone 8. If I try to see predicted for zone 12, which was a much easier to predict. So as you can see in zone 12, which was a bedroom, the temperature swings were not that high. So the temperature was way near to the set point, which was around 21 degrees. So if I plot it with the actual, I see that it's able to predict good. Sometimes it's predicting too much when it's not supposed to be like this. But the difference is not that much. It's all within 1 degrees. So 1 degrees is still good. And even the prediction which is happening for 1 degree is just for 1 or 2 time steps. So it's not that long bad prediction. Uh, if I try to see how it was with the 48-hour prediction, 48 time step prediction, which was um, 12 hours in ahead. There we see that it's able to capture the overall peaks within half a degree range, but then it falls short when suddenly there are drops in the temperature. If we see the zone 12, which was much harder, and for next 48 time step, so we can see that. So here we are comparing predicted versus actual for zone 8, which is with a lot of swings. So here there it's not able to predict very well. So here, so this now the point is this data I've showed you is with 2 zones and with less inputs. My actual model has all the zones in the building. So when you have all the zone temperatures in the building, so model kind of understand that temperature of zone 8 is somehow related to the adjacent zone. So it learns from that data also. And there the prediction was much better. But at least for today, it's just showing you how it looks like. Yeah, I think I'm done. Uh, Now we can go through if you guys have any questions, practical questions or something theoretical questions.
Yeah, thank you very much. This is very nice presentation, very nice work. What about state of art in this
Yep.
area? What
State of the art. So yeah, so probably there are very few people who had worked with LSTM, and I think I'm only the third or the fourth paper or the person PhD right now who's working with this, because LSTM is also very new, not very new, but relatively new in terms of Keras and how libraries have developed. And I think there are just 2 PhDs I know. One is from Canada and one is from Stanford or somewhere. I think from Stanford, who is working with data-driven prediction. So my topic is currently a very hot topic in my field, and people are trying to learn multi-zone prediction. So predicting one zone in a building, for example, it becomes a multi-input single output, MISO model. So that was easier till now. But MIMO model, which is multi-input and multi-output, and that becomes multi-zone modeling. So that is a new hot topic right now.
Yeah, yeah, this is very good. So thank you very much. Any other questions from? No questions? Are you watching us or?
We are watching, yes.
Okay. Any other
Yeah,
any
we're
questions to this nice presentation?
Yeah, it was very nice.
Yeah,
Congratulations.
very good. Thank you very much for this great work. Yes.
Okay.
Um,
Yeah. Then if people don't have other questions, then I think I can stop sharing. And
yeah.
yeah,
So thank you very much.
yeah.
Thank you very much for this nice presentation.
Thank you.
So